Yeah, find the area of this function over the region. Yeah, let's draw this sketch a little bit. Yeah, so x, y, and z. So we don't need a good diagram to so this is a circle centered at the origin with radius r 4. This is 4. This is the region. R is this one. R is this case R is your sigma. Also we have sigma. Okay, sigma. Uh, yeah. So take a small so infinitesimal area which is dA. I think look at the geometry. This geometry is circular. So then it is so we better use which one? We better use the circle. So look at this region. Region is circular. Yep, circular. Then so do we use rectangular coordinates? I think it is easy for us to use which one? Which coordinate system? It is called because this is circular geometry. So this is circular, right? So which one is better? Our geometry is circular. Yeah. So without using sine and cos. Yeah. So without using rectangular or Cartesian coordinate, you better to deal with r theta. Remember r and theta. Yeah, polar coordinates, using polar coordinates. Yeah, dA. So then using dA can be written expressed in terms of r and theta. Remember last time r d theta dr. So this is the infinitesimal area in this in this of this infinitesimal bit, and here so this is the corresponding infinitesimal. So let's denote d sigma, lowercase sigma. Yeah. So what is the relationship between dA and d sigma? Remember. So what is the relationship between d and d sigma? D sigma is equal to d sigma is equal to magnitude of the normal vector, to this the normal vector times dA. dA is r d theta dr. Yeah. So how do we find the normal vector? Right. So do you know how to find the normal vector? X, Y, and this is Z. What is this? Z, you can take Z to the other side. X, Y minus Z is equals 0. What is this? G of X, Y, Z. This is a level surface. This is a level surface. This is a level surface, right? So the normal vector to this level surface is what is, so this is a level surface. What is the normal vector to the is gradient of g, right? So which is partial with respect to x, which is y, partial with respect to y, which is x, partial with respect to z, which is 1. Okay, yeah, this is the normal vector. Then magnitude of this normal vector would be 1 plus x squared plus y squared. So if you use polar coordinates, right? Polar coordinates, x squared plus y squared is equal to x is r cos theta, y is r sin theta. Yep, x squared plus y squared. What is x squared plus y squared? R squared, right? Yeah, this is same with square root of 1 minus 1 plus r squared. So this is your normal vector. Yeah, so this is the conversion. Yeah, d sigma. Yeah, d sigma is equal to 1 plus r squared. So r d theta dr. So now, yeah, so you know this one, then what is that? So what is that theory? So don't you remember? Don't you remember? Don't remember. So this one here. Here we go. Level curve. So 3 dimension. If you have a So how do you find the level surface? So if it is equal to constant, then you have. So if f is 2 dimensional, you get level curve. If it is 3 dimensions, you get level surface, right? So the function is equal to constant. The function is equal to a constant here. So g, so this is a level surface, right? Then grad of f is perpendicular to level surface, right? So that is d sigma. D sigma is equal to d theta. Which one? Which one here? D sigma the theta. So this is the normal vector here, this one. Magnitude of the normal vector. So normal vector is this. The magnitude of the normal vector is square root of 1 plus r squared. All right. This is the magnitude of n normal vector to the surface. And this is your dA. dA is expressed in polar coordinates r d theta dr. Got it? Make sense? Right? Yes. Now we integrate. This is integrate over sigma. This is integrate over this region. This is our region. Circular region. And let's assume the surface integral. Yeah, so this is so this one. So you don't get these things, only the surface area. So which is uppercase S. And you can put limits. You can put limits of this one. So let me rewrite this nicely. A double integral over the region R. So region R, so we know the variation. So region, so radius from 0 to R. So this is a region. If you want to get this region, you have to change R from 0 to 4. Yeah. So R is changing from 0 to 4 and theta 4. And theta, so what is the variation? So what is the range of theta? Theta from where to where? So if you want to get this full circle, yep, so from 0 to 2 pi, yep, 0 to 2 pi, 0 to, so theta is 2 pi. Yep, so R and theta are independent. Yeah, you can integrate this very easily. Theta 0 to 2 pi, and there is no theta 0 to 4. Yeah, you know how to do this. So you can find this. This is 2 pi. 2 pi times this. Yeah, so that gives you the surface area of this one here. So like that, yeah. So you had to do a couple of questions to compute the surface area. Then you can get some experience. You can get experience very easy, right? First, so all you need to do is if you understand, if you remember this one here, so this one basically. This one, sigma d sigma is equal to magnitude of the normal vector times d, and integrate both sides. This is over the surface sigma, and this is over the region, over this region, and this is sigma. Then you get the so the surface integral of the entire surface area. Got it? So makes sense. I think you had to solve a couple of questions, first problems. Then you can very easy over here. So I will give a couple of questions and spot test. Yep. So this weekend, you have time. So practice these problems. I will upload a tutorial. 1 or 2 questions. Then you are ready to take any questions. Yep. Any questions? So you know how to parameterize a surface, right? So sigma can be parameterized using 2 variables, 2 parameters, u and v. So this is the parameterization, right? So so we write sigma in terms of u and v, and this is the x component, y and z, right? And you have sigma. This is your sigma, and and in some region are in 2 dimension. So so like this. So this is your sigma here, and this is your region in 2-dimensional space. So and you have this relationship here. So dA is equal to, no, d sigma is equal to magnitude of the normal vector times dA. That is the conversion, right? So you have that. All right. So be the positive vector, positive vector for any point on sigma. and f is a scalar value function or real value function defined on this, in R3, So if you have a scalar value function defined in R3, that means it is defined in this region, So this surface, that function is defined on this surface, right? F is a function. It is defined in R3. That means f is defined on this surface, right? Okay. Then the surface area of the surface integral of f over sigma is equal to, so this is the surface integral of f over sigma is equal to, your f, you have to write your f in terms of u and v times that unit magnitude of the unit vector to the surface times d sigma. D sigma, this is dA, this is dA. So here you integrate this one over that region R. So this is the surface integral in a scalar field. Make sense? So if you have a, let's say if you have a surface and you know the temperature of the surface, right? So you can find the average temperature over this surface by computing. So that means you have this surface, right? This has an equation, right? Now you define the function for, this is a temperature function on this surface x, y, and z, right? So now you are asked to find the average temperature over this surface. How do you find? So you have to integrate the temperature function throughout this surface. The surface sigma and small bit is d sigma. So which is same with? So same thing here. Here look at this. Same thing here. So here the function is equal to 1 here, right? That function, if you have a function, some function, so you have to put that scalar function here. Then you have to multiply this side. So let's say if you have function, scalar valued function defined on this sigma surface, right? So let's say temperature on this over this surface, right? So find the average temperature over this surface. How do you find? So here you have a surface, so which is sigma. So this is sigma, uppercase sigma, and so here I define a function on this sigma, right, on over this surface. So I know the function of the temperature at any point on this in this surface, right? So which is this one. So if you are asked to find the average temperature over this surface, then you have to compute this integral, double integral. So how do you compute? So you have this identity one, yes, d sigma is equal to magnitude of magnitude of normal vector times dA, right? So d sigma is written in, yeah, so this you have to write T in terms of U and V, right? UV, right? And you write this d sigma in terms of, yeah, so you have this conversion, magnitude of normal vector times du dv, right? This is over the region R. So this is the, yeah, this is, yeah, so this is the surface integral in scalar function, right? So this is the surface integral of T, right? T is a scalar function like temperature, right? Yeah, does that make sense? Did you understand? Yeah, did you understand that? Previous. Yep, so let's evaluate the surface integral. So the vector field is given, okay? And the surface is given. Look at the surface. Sigma is the part of the plane. So let's write. Let's draw a small diagram. Z. X plus y plus z is equal to 1. Yeah. And x is positive, non-negative y and z also. So we have to consider the first code, octant. Yeah, octant. This is called octant. Yeah. So, yes. This plane. So this is the plane of sigma. Sigma is, yeah, sigma is x plus y plus z minus 1 equals, yeah, this one. So this is your sigma plane, right? Yeah, this is sigma. Yep, so n is the outward unit normal. Yeah, very easy to find because this is a plane. Yeah, very easy to find that. Okay, y. We'll look at this. X plus y plus z, which is a constant. So this is a level surface. Level surface of G, a level surface Y, it is a constant. Then the gradient is perpendicular to the surface, which is 1, 1, 1. Got it? So this is 1, 1, 1, and if you want to find the unit unit normal, yeah, so it's divided by magnitude, which is square root of 3. All right, this is the unit normal to this plane. Okay, we found that. And what is, yeah, let's write this one in terms of u and v. Yep. So x is equal to u, y is equal to v, and z can be written in terms of u and v. 1 minus u, 1 minus v, right? And what are the range of u and v? Yeah, so what are the ranges? Yep, so this is 1, I think this is 1, 1. Yeah. It is given that the outward normal point towards the positive z. Yeah, should we take n as k? No, no, no. So outward, going outside, yeah, going outside. This, if you have a surface like this, so outward means you have this one here. Inward means, yeah, inside. This is going outward, yeah, right? Going outward. So this is unit outward, unit normal, no, unit normal outward vector. Yeah. So let's check the boundary. X varies from 0 to 1. Okay. So this is your sigma plane, and this one here, the shaded. Uh, what is this? This is our R. So which is yeah, which is in this OXY plane. Yep. So this is our R, right? This is our sigma, right? So take a small, take a infinitesimal, yeah, area. So which is d sigma, and the corresponding two-dimensional one is dA, right? Okay. All right. So let's put terminals. X varies from where to where? 0 to 1. Then U varies from 0 to 1. So these are the boundaries. Then let's pick a general point here. Then Y varies from 0 to. So this is what is the equation of this? The equation is X plus Y equals 1. So the y varies from 0 to 1 minus y, 1 minus x. So y is v varies from 0 to 1 minus x, x is equal to u. Yeah. Yeah, so these are the boundaries of u and v. Right, we identified that one, and we know the conversion. What is the conversion? Yeah, d sigma is equal to yeah, magnitude of unit normal vector, yeah, times dA. So here look at the shape of R. So it is a rectangle shape. Yep. So here you have a corner. Yep. So I think we better use rectangular coordinates. Yeah, you don't need to use. Yeah. Let's keep as it is. Yep. We don't need to think about polar coordinates. Yeah, so this is rectangular coordinates, x and y. Okay, so right, so we have this conversion. Let's find. Okay, yeah, d sigma is equal magnitude of n. So what is the magnitude? Square root 3 dA. dA is du dv. Right, so this is the conversion. Okay, so we know the velocity, no, vector field. Vector field is F. So written in terms of x and y, I would like to write that in terms of u and v. Yeah. So yep, uv. No, can we use directly x and y and z? Yeah, you can use. Yeah. So someone is asking, yep. So can we use directly x and y? X and y, yeah, you can use because you are small kids. Yeah, that's why I use u and v. Some people, get confused. Yep, some people get confused. Yeah, you can use a x and v, x and y only. Yep. Yep. So good question. Yep. Yeah, y is equal to, yeah, v and z is equal to 1 minus u minus v. Yeah, so that is x component written in terms of u and v. Yeah, I will write this one in terms of u and v. X is u, other one is z, is that term 1 minus, and the third component xy, uv, right? Yeah, uv, okay. All right, so we have to find the, yeah, perpendicular, yeah, so normal component of this velocity vector. So we know that u is this one, then, yeah, so when you find that, yeah, 1 over square root 3, sum these things up. Oh, I don't like to write, minus u minus v plus u minus u minus v plus uv, right? Right. So this is the, yeah, normal component of velocity or vector field. All right. Okay. Right. So, okay. Count that. So now we have this scalar function, right? Okay. This becomes scalar. Yeah. This is a scalar. All right. Now we are going to find the flux across this surface, which is this. This is same with, we know that, what is the conversion? D sigma is d sigma is d sigma, yeah, da no, normal, magnitude of normal, unit normal, what was that? Yeah, magnitude of that is square root 3. This one, d sigma is this. Okay, this, that is the conversion. Then that, yeah, started. D sigma, yeah, can be written in this way, scalar sigma. Yeah, we found this bit. So this would, yeah, this is a scalar function. Yeah, yeah, and we rewrite this one. So let's put this one. Yeah, so you have to put this garbage here, everything there. Everything there, 1 over square root 3 times that thing in terms of u and v, right? And d sigma is equal to, yeah, d sigma is square root 3, yeah, square root 3 cancels, yeah, square root 3 du dv. Yeah, so you know the limits of u and v. Yeah. Yep, so u varies from u and v are independent, x and, like, yep, u one. But depend, right? You look at this. Yeah, u is the independent variable. That's why it is the outside. So I put u outside, and but u v depend on u. Yeah, so v varies from 0 to 1 minus u. Yeah, if you integrate this, yeah, so you have to put that large scalar function here. Simplify this and integrate. Then you will get the answer.